That was Claire de Lune by Claude Debussy and arranged by Kathy Peck. This is a Lion Healy Creo Lever 40 harp. So I have to check my levers for keys. And that was the Moldau by Schmutna, also arranged by Kathy Pett.
Thank you very much, Kim. I think we
You're
are on time
welcome. Are we
to
all
start the
on
meeting.
time?
So,
Thank you so
Barbara,
Yes. Am I coming through okay? We're
all
dealing with a
good.
new microphone. Okay. Thank you very much, Kim. That was lovely as usual, and we really appreciate your contributions to all of our meetings. And people were actually able to hear some of it here,
Oh,
which
thank
isn't
you
always
so
the case.
much. I'm glad it worked even without the original sound. Thank you.
Yeah. Well, take care. And welcome everybody to the May meeting of Orange County Astronomers. It's good to see all of the people that are here in the auditorium, and I can't see those that are attending online, but welcome as well. We have a really great program as usual tonight. And without more ado, you're going to have to put up with me for the announcements, and Sam is getting them lined up. Okay, we're ready to go. Can't hear? Can you hear now? Can you hear? Okay, great. Yeah. The problem is that I am used to gesturing somewhat with my hands, and that's not good when I'm holding a microphone. So sorry. Anyway, as I said, welcome to the meeting. And yeah, we have some new members. Chester Ainsworth, Eloisa Burton, Brad Feiner, who actually I believe is a returning member, Aiden Hahn, Alexander Ketchum, Arnav Mishra, James Paligra, and Richard Witt. Are any of you here in the auditorium today? Not sure I see any hands. Anybody who is coming live to the meetings, Charlie brings the membership badges and has them available here. So please check the whiteboard in front for your membership badges. Otherwise, eventually he will be mailing them to you when he figures you're not going to show up. Welcome, as I said, to the club. We hope that you really enjoy your membership. And please do talk to the other members around. We're a friendly bunch. We like meeting new people, and we like greeting each other as well. We have the wonderful Cosmic Coffee Corner for those of us that are here on the ground. It is up on the upper level. And I saw somebody with a donut tonight. Helen and Doug are away for the this meeting, but Karen is handling the honors up there, and we thank her. We do have the star party coming up for Anza. The last two star parties got clouded out. That was a real bummer. And actually, we had rain for one of them. The next Anza Star Party will be May 24th. The odds are getting better for a clear night. So hopefully we will be seeing a lot of people out there. We are still working on getting the Orange County Star Parties online, and hopefully we will have news for you about that before too much longer. Our special interest groups, the Astrophysics SIG is meeting on June 20th at Orange Coast College. That has been a very successful meeting area. It is if you're at all interested in the why of astronomy, that is the SIG to attend. The Astro Image SIG has gotten back to in-person meetings, also at Orange Coast College. Their next meeting is June 6th. And I know there were a lot of imagers that were interested in getting back and sharing stuff in person. So if you're at all interested in that, check out that meeting as well. Beginner's class, for those of you who would like to know a little bit more about our hobby, maybe you're just getting into it. Maybe you've got equipment you aren't quite sure what to do with, or you are trying to think about what you want to get, what you actually want to do and focus on in the hobby. The beginner's class is a great resource. The next session of that is June 6th. And then I believe the July session is the Bring Your Telescope class, which if you want help with the telescope, that will help take you through how to set it up and all that sort of thing. If you are willing to volunteer to help out people that need some assistance in that area, we can always use volunteers for that as well. The OCA board meeting was actually last Sunday, and we have them every 2 weeks. I'm sorry, every 2 months. Every 2 weeks would be way too often. So the next one is July 13th, and we have them online. So if you're at all interested in seeing what goes on with the management of the club, just email Alan Smallbone, and he will be happy to send you a link. Okay, we have some upcoming events. The Mount Wilson Observatory is they have a program, Mount Wilson Observatory Presents, the Saturday Evening Talks and Telescopes. So the Saga of the Sphere is coming up, and these talks are all they're always a lot of fun. So if you are interested in an astronomical event outside of the club, that's a great one to attend. Our I should say our Doug and Helen's annual, well, at least annual excursions out to the great patch of giant radio telescopes out in the Owens Valley is coming up, the Owens Valley Radio Observatory. That next one is on June 20th. It's always a lot of fun. He has a lot of contacts out there. They have tours and other things that are set up. Unfortunately, as I said, Doug can't be here tonight, but if you are at all interested in it and haven't talked to him about it already, shoot him an email. His email is down there at the bottom, and he will be happy to fill you in on details. As I said, our How to Use Your Telescope class is coming up July 7th. This time it will be at the Orange Coast College facility, the same building where we have been having the SIG meetings. It's Building 40, the Astronomy House. And if you have any questions, want to volunteer, whatever, the contact information is on our contacts page. The How to Use Your Telescope class is always a lot of fun, and I really encourage you to go out, whether you want help or you want to give help. Yeah. And the next, the class after the How to Bring Your Telescope class would be at the beginning of August 1st, actually. It is the basics of astrophotography. And that one that's also going to be at Orange Coast College in Building 40. And people have always found that to be very informative. If you've thought possibly that astrophotography might be something you might be interested in, that would be a great way to get your feet wet. Without any commitment or anything, just, go get some information, ask some questions. Our Adopt a Scope program. It has been a great success. And Jake, who's over here, has been doing a great job of refurbishing various scopes and other equipment that we have had donated to us. He has quite an inventory at this point. Are we going to be raffling something next month, do you think? Okay. We are planning to have one of these wonderful scopes raffled for the people that are here in the hall next month. So if you are at all interested in possibly winning a telescope, be here or be square for the June meeting. Outreach events, Martin Christensen is the person to contact. Again, his information is on the website. Under his leadership, the outreach program is coming back gangbusters. We've got a lot of interest in it from various schools and so on, and it is just really great to see it coming back to life. And thank you very much, Martin. Yeah. I don't think you can hear me, but Martin was just saying that we've already got bookings starting for next year. And the first one, you can see some of the calendar dates coming up on the screen. We do have a few left for like this year, and then our really busy season usually starts up after September. And if you're volunteering for outreach is a great way to spend an evening and really feel rejuvenated and refreshed afterward. So I really recommend you think about seriously volunteering and getting in contact with Martin to figure out which outreach events you want to go to. Thanks. The Serious Astronomer. You may have noticed that we really have gone all electronic, and that is allowing Dave Fisher, our editor, to have a lot more freedom in how he's thinking about doing the newsletter, since he's not bound to the physical constraints of pages and a certain number of pages per edition. So I do hope that all of you are checking it out on our website. Notices are going out about when it is available. And the material in it is great. All of the stuff that you have enjoyed in the past on the paper copies, it's in the electronic copies, and we are hoping that we'll be able to do more to have pictures that you can actually see, in color and detail and all this sort of stuff. Maybe links to great things just directly. It's a great opportunity, as well as something that turned out to be a budget necessity for us. And if you are at all interested in, I see a hand up, sir. Which microphone are you talking about? I don't know what's being picked up there. Sam will try to check into it. Thank you. Okay, we've got a vagrant microphone click problem here in the hall, and we are attempting to get that resolved. Anyway, if you are interested in submitting material for consideration for the Serious Astronomer, definitely get hold of Dave Fisher. Friendly reminder for all members who use the ANSA site, please lock Anza house. Make sure Anza house is locked before you leave and the windows are closed, and close and latch the gate before you leave the site. If you have used the restroom up at the observatory, please be sure that's locked as well. And of course, if you anything that you bring with you, take away. We do not have trash service out there. And the other thing about Anza is we are just about through with our fire clearance project. You will see a lot more cleared areas than may have been the case last time you were out there. The crew that did the work they did an incredible amount of work, and the result is that I think we are probably in a safer position fire-wise than we've been during most of the time I've been in the club anyway. And it's up to us now to maintain that so that we keep our edge against some of the elements anyway. That goes for the weed clearance. We still need to watch out for grasses and stuff. They're going to be growing. We're going to have gourds growing. We're going to have other stuff growing. The point is to keep it away from structures, keep it away from anything that might be endangered if flames got too close. And I don't know, tonight's moon phase, it says full moon, but 91% illumination does not sound to me like entirely full. But full moon is coming. The next club meeting is June 13th, 2025, and I trust that we will be seeing everybody here. Remember, that is going to be a raffle night, and those are always fun. And without more ado, I think it's time for the What's Up program. And Raisa, you want to take it from there?
Sure. Thank you very much, Barbara, for the announcements. Alex,
I'm ready.
please let us know what's up in the night sky.
Okay, here we go. Should be saying San Francisco, and here we go.
Yes.
Yeah, down here. Click. Click. There we go. Hey, it's good to be back. It's always good to be back, and thanks for having me here. Thank you, Barbara, for the introduction. Thanks for having me here to tell you about what we have to look for in the next month. We're going to start in our neighborhood and then head out as we go. Here's what our closest neighbor is doing. Hang on for a minute. I have to adjust where Mr. Zoom is. There he is. As it goes around in its elliptical orbit, you can see it's going back and forth, closer and further away from the Earth. This causes libration, the rocking back and forth, that it allows us to see some 59% of the surface area. And here you can see how the moon is closer or further from us as it follows that elliptical orbit. See how it grows and shrinks depending on how far away it is? Well, when the moon is closest to us, it's about as big and bright as it can get. We call it a supermoon. When it gets farther away, however, and it's full, it is much smaller, and it's sometimes called a micromoon. Supermoons are, in fact, about 14% bigger than and 30% brighter than micromoons. This month, our moon will be a micromoon because it's about as far away from the Earth as it can get. Let's go. Time for the next slide. Thank you. Monday night, May 12th, you will see the small but full flower moon. We call it that to reflect the blooming of spring flowers across North America. It's going to be the final micromoon of 2025. Now, May and June will not be a great time for comet watching. Comet 2025 F2 Swan at magnitude 5.5 is the only comet brighter than about 13th magnitude. And it's near the Pleiades, which will be close to the rising sun. So it's not going to be a visual treat. And nor is it a great time for meteor showers. May's big meteor shower was last Sunday, the Eta Aquarids. And the next big one won't be till the Boötids, which won't be until the 27th of June. So next month's What's Up guy gets to tell you about that. Just to give you meteor fans something to look at, though, I would like to point out to you, just a second, here we go. I'd like to point out to you that this is one set of pictures that I get from my meteor cam. And every little streak you see there is a meteor flashing over Moreno Valley, or most of them are. My cameras are 2 of hundreds set up wherever they can find volunteers around the world. And they're looking for more volunteers right now. So if you want to help, get in touch with me. It's a scientific endeavor in that all the stuff is collected and available for scientists to check how meteors are doing and so forth. This is the Southwest, and you can see there's a big group in New Mexico. There's another big group in Arizona. There's not too many of us out here watching out for the Southern California area for these. So if you want to join up, contact the globalmeteornetwork.org or get a hold of me. This is a great time to be doing something with sunspots. You can see that we're past the peak, but we still got a lot of sunspot activities. I'm taking advantage of this high level of activity to do something with the sun. As you know, I've told OC about this. I love the Astronomical League because I'm a lazy guy and this gives me discipline. I need a checklist to keep me motivated and on task. And the Astronomical League observing programs are just that. They're organized observing lists that they kind of add structure to you and direction to your observing. You know, no more standing around in the dark wondering, I don't know, guys, I don't know. What do you want to look at? What should I look at tonight? Hey, is M42 up? Yeah, there are some 70 programs in this. And for a long time, they were just for visual observers. And if you did enough of their projects, you were considered a master observer. But now there are also imaging programs, and one can even earn the title of master imager and learn stuff while you're doing it. So I started my imaging program with the Sunspotters Club program. Now, I'm not the world's best solar imager, but I have had a lot of fun collecting this data, and I can do it from the backyard. Here you see a group of sunspots moving across the sun when images are taken a few days apart from each other. You can see how they develop and grow and so forth. Now, in this program, you have to take at least 20 images of the full solar disk over a period of 2 rotations of the sun. It's about 2 months. And then you have to identify the features on the solar surface and classify the sunspots as to the way they're built, their size, and the way the sunspots are distributed. So for every day, I have a report that looks like this. It has a solar disk oriented towards solar north, and that was a big problem in itself. I had to learn where is north on the sun? It's hard to tell. There's no continents up there, you know. Some data, including how our experts count the sunspots, over here, the groups, locating them north or south of the equator. You have to calculate the Wolf sunspot number. You learn to classify sunspots and groups according to the modified Zurich class. Now, believe me, I did not know what any of these fancy data points were. I didn't know they existed until I tried this Astronomical League program. And now I'm nearly a solar expert. Well, not really, but I do know a whole lot about what solar scientists do with some very simple parts of their task. For those of you who like to see when celestial bodies are close to one another or far apart, here is a list of syzygies and other such things. One of them is the best time to observe the shape of Venus, as it will appear to be separated from the sun by its greatest elongation the morning of June 1st. Of course, some of these are daytime events, so you're probably going to miss them. There is, however, one daytime event that could make for a pretty cool challenge. Point your binoculars to the moon a little after 2 in the afternoon of May 23rd. You could well pick out the moon and Venus during the daytime, if you're lucky. Now, we've all seen the moon during the day, and many of us have seen Venus during the day. Maybe you can catch this conjunction. You know, this is a very nice picture, very impressive, but our May 23rd event will have a lots more separation at something like 3 1/3 degrees. At any rate, If on the Saturday of the next new moon weekend, you find yourself out in Anza at the club star party, go hunting for your planets. Jupiter will be following the sundown. See, right behind this tree. Mars will be a little higher in the western skies. In the early morning, Saturn and Venus will be up. They'll poke their heads up above the eastern horizon. Yeah, you're right. The planets are not the highlights this month. Most of them are in the sun most of the time, and they're not displaying all that much in the dark. So we move on to deep space, the realm of the really big, but far away and probably very dim objects. So bring out the cameras or a big Dob if you have one and go star hopping. Our first deep space highlight is Messier 102, so-called the Spindle Galaxy. Up in Draco, it's small and it's not too bright, like when I was a kid, at 9.9 magnitude. And remember, 9.9 magnitude in a galaxy is a lot dimmer than 9.9 in a star because that light is spread over the whole area of the galaxy, not gathered in just one pinpoint of the star. Of course, if you don't have a camera on that telescope, you'll not see this big, beautiful color image here. You're going to see these little shades of gray with the core a little brighter and the edges trailing off. These highlights that I'm giving you are both photographic and visual objects, but they look substantially different in the camera than they do with the human eye at the telescope eyepiece. My suggestions for this month came from a source that had unusual names for the various objects. M99 is called St. Catherine's Wheel. The rest of us call it the pinwheel. It's up in Coma. St. Catherine's Wheel, well, it's a torture and execution device. You put the adulterer or rapist or saint, if you're killing saints, the infidel, and you turned it as a way of inflicting punishment. It later also became a type of firework, popular among other places in Malta, where there is a special celebration of St. Catherine's Day, celebrated, of course, with those fireworks. M100 is here called the Mirror Galaxy, but my source also called it the Blow Dryer Galaxy. It's a little larger and a touch brighter at magnitude 9.3 than the other two earlier galaxies at 9.9. It can be observed in 20 by 80 binoculars, but you'd be happy with the big telescope. M63 is bigger and brighter than all the other galaxies we've seen so far, at nearly 4/10 the size of the full moon. You can see it with binoculars as just a hazy patch of light. But as with all of these, a good telescope will work wonders. It's also in Canis Venatici. The Sculptor Galaxy, NGC 253, that's one of the most easily observed galaxies after the Andromeda Galaxy. It's about 3/4 of the size of the moon and fairly bright at 8th magnitude. M106 is an intermediate spiral galaxy. It's one of the largest, brightest nearby galaxies, but it's intrinsically similar in size and luminosity to the Andromeda Galaxy, but it's further away, so it doesn't look as big to us. It's bright enough to be spotted with 10 by 50 binoculars as a faint patch of light. I always think that it's the area where there isn't anything there until I really get adjusted to it. Through small telescopes, you'll see the galaxy's brighter center, while large telescope will reveal its brighter structure. The Cat's Eye Galaxy, M94, is also called the Crocodile Eye Galaxy. It's a barred spiral galaxy. It's about the brightest member of the M94 group of galaxies in the constellation Canis Venatici, which contains about 20 galaxies, several of them that we've seen tonight. Now, okay, you're asking me, why are all the highlights galaxies? Why? Well, because we're pretty much in the middle of galaxy season. You see, we live right about here. And as you can see, during summer, we point in towards the Milky Way. So we can see all the things in the Milky Way, nebula, gas clouds, globular clusters, and open star clusters to see. But in winter, we're pointed outwards, and there's just not that much in the Milky Way out here. So we don't see much. So in the winter, we're still looking through the plane of the galaxy, but outward. During the fall and spring, however, we're looking above or below the thin disk of the galaxy. So we're looking up and down and not into the disk, into the vastness of extragalactic space itself. And there just aren't many cool Milky Way things to look at, bright nebula globs and such. So we are left with galaxies. It's galaxy season. Now, NGC 3372 is one of the largest nebula in the sky. It's 4 times larger than the Orion Nebula. It's near the heart of the nebula lies Eta Carinae. The Carina Nebula is so big and bright that you can see it with the naked eye. The hitch in seeing this highlight is that you would have to be much further south than we are around here. I'm just showing it to you because 2 weeks from now, it will be my highlight as I observe from San Pedro de Atacama, Chile. So I thought I'd tell you that. And I cannot leave you without reminding you that Adam Block will be doing an imaging workshop at nightfall this next October. For you astro imagers, this should not be missed. And of course, everybody enjoys a star party with the resort and a pool, a barbecue, a bar, and all the other fun stuff that happens at nightfall. I understand the hotel rooms are already taken, but there are a few RV spots and lots of other places left out in Anza Borrego to find a place to stay. And you're all welcome at nightfall, whether you're staying at the hotel or not. And there are a few spots left in the Block workshop. So make your arrangements if you haven't already. You can see the nightfallstarparty.com will get you started. And that, folks, is my presentation. So I hope you have a good time this next month. Thank you, Reza. And let's see, get out of here.
Thank you very much, Alex. What a great presentation, entertaining and informative, and we learned a lot. Thank you very much for joining us and giving us this presentation.
You're welcome. Can you stop by sharing? Have you stopped by sharing?
Yes, we got that. Okay, so without any further ado, let me go into introducing our speaker tonight, who has studied physics at the University of Hull and obtained a PhD in astronomy at the University of Manchester. He has held research positions at the Max Planck Institute for Radio Astronomy and the Canadian Institute for Theoretical Astrophysics at the University of Toronto. He is currently an assistant professor of physics and astronomy at Union College in New York, where he leads research into pulsars and fast radio bursts. He is also a big music fan and avid gamer. Please join me in welcoming Dr. James McKee. Dr. McKee.
Thank you very much for that nice introduction, Reza. So would you like me to share my screen?
Yes, please.
Okay, one sec. Can everyone see that?
All good.
Can you see the laser pointer as well?
Yes.
Excellent. Okay, well, in that case, thank you very much for inviting me to come and speak to you. It's a shame I'm not there in person, but who knows, maybe I'll make it over at some point and be able to join you for one of your star parties. So I'm Dr. James McKee, and I'm a radio astronomer. Specifically, I'm a time domain radio astronomer. So I don't take these stunning 2D images of the sky like the ones we just saw that are going to be visible from your part of the world. Instead, I point a telescope at a patch of the sky and I see if I can detect repeating signals. You could think of it as being like looking at the sky with a single pixel. Much of what I study are a type of neutron star called a pulsar, and I'm going to tell you about those briefly. Is this going to move? Does this want to move? There we go. Okay. So some of you will know who this is, but for those of you who don't, this is Jocelyn Bell Burnell. And in 1967, she was a PhD student at Cambridge University in the UK. And she was working on the construction and operation of this telescope that she's being photographed in front of. It was called the Interplanetary Scintillation Array. So it might not look much like a radio telescope to you, but designs like this are still used today. These ones that aren't quite the same as like the big radio dishes that we're used to seeing, but Anyway, the signal that Jocelyn Bell was looking for was predicted to be like random fluctuations in brightness of radio sources. But as she was working on this experiment, she started to notice these extremely regular periodic signals in the data when the telescope was pointed at a particular patch of the sky. And these signals weren't random at all. They were very, very regular pulses, repeating every 1.337 seconds exactly. And the fact that these were coming from the same coordinates on the sky ruled out the possibility that they were from a source on the Earth, like a radar or something like that. And the source also couldn't be something like a geostationary satellite. Those have to be located directly above the equator, and this source was in a totally different part of the sky. Other telescopes around the world were also able to detect the same signal, so they could rule out some kind of instrumental effect that was causing an erroneous signal or something like that. So that meant that there was this previously unseen signal coming from somewhere in space. And it would have been pretty hard to discover something like that and not think it could possibly be aliens. I know I would probably think it was aliens if it was me detecting this for the first time. But I've actually been to talks by Jocelyn Bell, and she claims that this was never really taken seriously. And the reason for that is that if the signal was indeed an alien transmission, it would be an amplitude modulated signal, so like AM radio. And the reason that we use frequency modulation these days, FM radio, is that it's much more robust against interference and it has a much higher bandwidth. So if an alien civilization was sufficiently advanced that it could broadcast an interstellar message, it would also understand that choosing an AM signal would be a bit of a weird choice. Is this going to move? Yeah, there we go. So what Jocelyn Bell had discovered was the first neutron star. Now, it was predicted that when stars of a certain high mass stop burning their nuclear fuel and they collapse under their own gravity, they would die and leave behind an extremely dense spinning core. So relatively low mass stars like the sun, they will leave behind a white dwarf. So that's the core that weighs about half of the initial mass of the star, and it has a size about that of the Earth, give or take. So that's really dense, like packing half of the sun's mass into an area just the size of the Earth. But extremely high mass stars are going to go supernova, and they're going to leave behind something else. The very, very massive stars that go supernova are going to leave behind a black hole. But stars that are somewhere in the middle, where they're massive enough that they're going to explode as a supernova when they run out of fuel, but not so massive that a black hole will be formed. Instead, these leave behind an extremely dense remnant called a neutron star. And these weigh about twice the mass of the sun, but they have a radius of only around 12 kilometers. And if you do the calculation, you can show that that is as dense as the nucleus of an atom. And this is why they're called neutron stars. The gravitational force is so strong that atoms get crushed. The electrons combine with protons to make neutrons. So these things, in many ways, are just like an enormous atomic nucleus. So when the core collapse happens in this supernova, the star is initially spinning. And when all of the mass suddenly gets crushed down into a tiny volume, angular momentum is conserved, and the neutron star gets spun up to incredibly high speeds. When they're born, they're spinning tens of times per second. And these objects also emit radio waves from their magnetic poles, which causes them to appear to pulse on and off. So we call the neutron stars that we detect this way pulsars. And to give you a sense of how small these things are, I looked up the area that you're all in California. And this is a neutron star to scale on a map of the Santa Ana area. So this is nearly twice the mass of the sun in a radius smaller than the distance that many of you probably drove to get here tonight. So as the pulsar spins and we see it appearing to pulse on and off, When we take a radio telescope and record a time series at a really high sampling rate, this is what we see, this like little trace at the bottom where we can see the blip every time the beam spins around and hits the radio telescope. Or rather, that's what we see in the very best possible cases, because most pulsars are very, very weak radio sources. If we want to detect them at all, we usually have to sum together many thousands of pulses, just stack those up until we can see something that emerges from the background noise. And the number that I carry around in my head for this is that if you took a cell phone and put it on Mars and called it, the signal that you would pick up from a radio telescope from that cell phone is about as strong as the signal we get from pulsars. So really, really weak radio sources, just like a cell phone on Mars. So these are not things that we can detect accidentally. And other than a couple in the Magellanic Clouds, we haven't been able to find any of these things outside of our galaxy. They're just too faint to detect. Even in Andromeda, the nearest galaxy, we just can't see any of these things. We know they are probably there, but when we do the calculation, we see that they'd just be far below the sensitivity limit of the current generation of radio telescopes. So while we think about how faint these things are, I'm going to show you what the radio sky looks like. And for context, though, I'm going to compare it to the sky in optical light. So when I give talks like this in New York, I'll usually show a picture like this, and I have to tell the audience that these things in the sky, they're called stars. And when we look at the night sky with our eyes, we see stars that are mostly really nearby. So like Betelgeuse in the constellation of Orion, that's about 550 light years away. It takes the light 550 years to reach us. And Sirius, the brightest star in the sky, is only 8 light years away. So what we see when we look at the night sky with our eyes are the closest stars to us. And these are all within our own galaxy. If our eyes operated at radio frequencies, the sky would look very different. It would look something like this. So nowhere near as busy as the optical sky. We see some points of light, and we see these weird shapes, like these kind of things here, these smudges. Those are clouds of hydrogen that are being energized by nearby stars. They're within our galaxy, so they're relatively nearby. All of these little pinpricks of light that look like stars are not actually stars. They're extremely bright galaxies, many billions of light years away, that shine very, very brightly in radio waves. So these are billions of light years away. It takes billions of years for the radio waves from these things to reach us. So think about that for a second. The optical stars are only bright enough for us to see the nearby ones. But these galaxies, billions of times further away, are so bright that they would be seen easily if we could see the sky in radio wavelengths. And they're so bright, by the way, because they have supermassive black holes at the cores that are swallowing up a large amount of material that gets superheated as it spirals into the black hole and releases an enormous amount of radio waves. Okay, so I'm here to talk about fast radio bursts, though. So I'll segue into that. And the story begins in 2007 when my colleague, Lorimer, was working in Australia. He's an astronomer. He's originally from Darlington, which is a town about 45 minutes away from where I was born in England. And he's a professor at West Virginia University these days. This is a picture of him playing with his bluegrass band called Almost Blue. And I just grabbed this off his Facebook. But anyway, Donk was searching for new pulsars with the Murray-Yang telescope in Australia, this radio telescope here. So remember, these are faint radio sources. You need extremely long exposures to be able to see them at all. But while Donk was searching for these things, he picked up one really, really bright pulse that lasted about 5 milliseconds. And what was really strange about this pulse was that it seemed to be coming from not just outside our galaxy, but far outside the galaxy. And the reason that he knew this was because the signal was dispersed. It was extremely highly dispersed. And dispersion is when light gets split up into the different colors that constitute it. So when you shine white light through a prism and you get a rainbow out the other side, the white light going in is dispersed in the prism. And the thicker the prism that the light goes through, the more the colors get spread out when they come out the other end. So exactly the same thing can happen with radio waves. Just it's the same physics. The only difference is that it's not a prism that we're shining, that the light is being shone through. So even though space is very nearly a perfect vacuum, it isn't completely empty. On average, there is a small number of free electrons per cubic meter. And the effect that they have on radio waves that pass through them is exactly the same as the prism on optical light. It's the same physics. It splits the radio waves up into different frequencies, and if the thing that you're observing is a pulse, this causes the low frequencies to arrive later than the higher frequencies. And the more space that the pulses had to travel through, the more free electrons that the pulse encounters on its way to the Earth, the more the frequencies get split up and spread out. So if this was a burst of radio interference from the Earth or close to the Earth, you would expect the signal at all frequencies to arrive at the same time. There'd be no dispersion, just the pulse would arrive at the same time, whatever the frequency you chose to look at it. So this is what's going on in the diagram. Pulses at high frequencies are at the top. Pulses at low frequencies are down here. And as you go lower and lower and lower, you see that this delay when the pulse gets received gets greater and greater. And this delay between the different radio frequencies gives you a way of estimating the distance that the pulse has traveled. So the delay is bigger if the signal has traveled further through space. And if you do the calculation, it turns out that this burst that was picked up accidentally from billions of light years away, well, it came from billions of light years away, pardon me. This was a flash of light that lasted less than 5 milliseconds, and it was detected accidentally from across the universe. And this is what the signal looked like. This is the actual experimental data. So you see this this dark line. That's the pulse being dispersed throughout the frequencies. I'm not sure how well you can see this, but we've got frequencies on this axis and just the time that the pulse was received on this axis. So the high frequencies up here. As you go to lower and lower and lower frequencies, the pulse gets delayed. And notice, by the way, that the time delay is tiny. There's less than half a second between the highest and the lowest frequency in this plot. So after discovering this, Don Lorimer and his team observed the same patch of sky for about 90 hours over the course of the year, and they never saw the signal again. And it was more or less forgotten about. That is until 2013, when a PhD student at Manchester University in the UK called Dan Thornton was again searching for pulsars with the Murray-Young telescope at Parkes, the same telescope, and he discovered another one of these things. See, this one's a bit sharper, but it's the same pattern. You just have this dispersive sweep that goes from the high frequencies being received first to the low frequencies being delayed and received later. So he had discovered another one of these things. And then he discovered another and another. And all in all, he detected 4 of these things. So I actually briefly overlapped with him. He was defending his PhD in Manchester the week that I arrived to start my PhD. So he was a tough act to follow. But anyway, this is the observational data for on the pulses that he discovered. And if you do the same kind of calculation, you measure the amount of dispersion that's been experienced by this pulse, you can see that, or you can calculate that all of the bursts must have come from billions of light years away. These pulse shapes in the corner, by the way, they let us see the duration of the burst at different frequencies. So it's about 10 milliseconds wide in this case. And because of these short durations, the phenomenon became known as fast radio bursts, or FRBs for short. So like the Lorimer burst, these were found to repeat. They, again, searched the same patch of sky for many, many hours and just came up with nothing. So fast radio bursts seem to be this bright flash of radio waves that appeared once and was never seen again, and were seen accidentally from across the universe. So this led to the interpretation that these must have been caused by some kind of extreme cataclysmic event. So black holes crashing into each other, or exploding stars, or something else that would just release an enormous amount of energy in the blink of an eye that would allow us to detect these things by accident from so far away. So suddenly the burst that Don Lorimer had discovered a few years ago was more than just a strange curiosity. There was now evidence that there is a population of objects causing these bursts, and that they were a new type of astronomical phenomenon that had never been seen before. So after Dan Thornton discovered the next set, he calculated how often one of these things goes off across the entire sky, just the event rate, and he estimated that about 10,000 per day go off across the entire sky. So with that in mind, let's look at the radio sky again. Now you might have to look carefully, but this is animated now, so you might see some little yellow flashes going off in the sky there. So before I showed you the still image of what the sky would look like if your eyes could see radio frequencies, now I'm showing you an animation of what the sky would look like if you could see in radio wavelengths and you could spot these fast radio bursts going up. You'd look up and you'd see these incredibly bright flashes going off like fireworks. So the duration of the burst is exaggerated here. In reality, they only last for a few milliseconds, but I didn't want to make it so you could blink and miss them. Now, you might wonder, if 10,000 of these things go off every single day, then why did it take so long for them to be discovered in the first place? Well, the problem is that telescopes can only see a really small patch of the sky at once, and many of you are astronomers, so you'll know that if you've looked through one, or if you've used a pair of binoculars, the way that you could think about it is when you go out to watch a meteor shower, you don't usually take your telescope with you. You just sit back and use your eyes to get a wide field view of the sky. And as most of you know, we talk about the size of objects in the sky in terms of their angle. And just to give you an idea of sizes, the moon is about half a degree wide. And the amount of sky a radio telescope can see at any single moment of time is about 5 times smaller than the full moon. So we call this the beam of the telescope. And in terms of the total size of the sky, the beam can only see about, what's that, 0.0005% of it. And if you do the calculation, if you say that there are 10 fast radio bursts per day, it means that if you spent 24 hours a day for 10 days straight pointing a telescope at a patch of the sky, you only have a 50-50 chance of catching one. So it isn't surprising that it took so long for this phenomenon to be noticed and then for it to be confirmed. It also didn't help that these bursts could easily be mistaken for radio interference. And in fact, for a while, there was still apprehension about fast radio bursts since they'd only been detected by the same telescope at Moryang. Other big telescopes around the world were looking for them. They were desperately trying to detect some of their own. But so far, they hadn't turned up anything. And it was worryingly so, in fact, to the point where people thought these might not actually be real astronomical objects. They might be some local source of interference or some bug in the telescope that mimicked the dispersive sweep of fast radio bursts. And this was further complicated when the Parkes telescope started picking up, or the Moryang telescope at Parkes, pardon me, started picking up a very similar kind of signal. So remember that we expect this dispersive sweep from things that have come from space, where the the high frequencies arrive before the low frequencies. And this is what we're seeing here. But it isn't exactly what we would expect. It doesn't quite follow the same kind of sweep that we'd expect. And we know mathematically exactly what a dispersive sweep should look like. So this was something similar, but distinct. And because of this unknown origin and the similarities with fast radio bursts, this new type of signal became known as peritons, which is named after this illustration here. It's a mythological creature that's a winged elk that casts the shadow of a man. So after these things started to pop up, a PhD student in Australia called Emily Petrov, and I've taken this from her Facebook as well, was looking into this, and there were a few things that she noticed about peritons when she started to study them. One of the things that she noticed was that you were much more likely to detect a periton in July than any other time in the year, which is weird. Like, why should that be the case? If this was something coming from far outside our galaxy, why should that source care that it's July here on Earth when we detect it? So another strange thing was that the most common time to see a periton was like the early afternoon, sort of 12:30 kind of time. So some of you might have some ideas what's going on here. Well, another thing that was noticed was that you tended to see these when the telescope was pointing in the general direction of the staff room. It's called the woolshed. So they were mostly coming from the staff room at lunchtime when people were microwaving their lunch. So it was found that if you open the microwave door before the microwave turns off when it's in the middle of its cycle, it can take the magnetron a few milliseconds to completely shut down. And the way that it shuts down mimics the dispersive sweep of fast radio bursts and causes this kind of signal. But why July? Why is that more likely to happen in July? Well, Australia is in the southern hemisphere and the seasons are flipped. So they like to do this thing called Christmas in July, where people do traditional Victorian white Christmas things in the winter months. And the idea is that, I don't know if this was ever proven, but the hypothesis was that people would take turkey in a dish into work and reheat it for lunch, and the dish would like bump the microwave as it turned around, and every time it bumped the door, it would just let out a periton. So going back to fast radio bursts, by now a few more telescopes had started to pick these up. And it was now well established that these were a real astronomical events and not just radio interference or some glitch in the telescope that initially detected them. So to recap, they come from billions of light years away. They last only a few milliseconds, and they seem to never appear again. And this led to the explanation that they were from something catastrophic, like colliding black holes, something releasing a ton of energy in almost no time. Or at least that was the case until a scientist working with the Arecibo telescope, Laura Spittler, found a fast radio burst that repeated. In fact, it was found to repeat 10 times in 3 hours. So remember that you can calculate the distance to these things from the dispersive sweep, so they were very certain that it was the same source. And this was a big deal because it completely rules out the idea of a cataclysmic event that was can't repeat. Certainly not on the scale of several times per hour. You know, you can't have a black hole collide with another black hole over and over again. You can't have a star explode several times in an hour. And I know what some of you are probably thinking, and yeah, they did check the microwave. It wasn't that. No, this was real. So we needed to think up some new explanations, and to do that, really, we needed to detect as many fast radio bursts as we possibly could. Now, the state of the art in fast radio burst astronomy is CHIME. This is a telescope in British Columbia in Canada, and it's one that I do a lot of work with. It's a little strange, unlike most radio telescopes. It's not a dish, it's these kind of 4 half-pipe shaped receivers, or or reflectors, pardon me. Those are about 100 meters long. On the long side is about 100 meters. This is an enormous instrument. And the reason for choosing such a strange design is that we can use this to see a lot more of the sky than a typical radio telescope can see at a given time. So CHIME can see 200 square degrees of the sky at once, which is about 1,000 times more than an ordinary telescope can see at a given time. And you can imagine that this has led to an explosion in new detections. So this graph here shows the number of, the cumulative number of fast radio bursts that have been detected over time. So we were gradually detecting them until about 2018, when we switched on CHIME, where we knew of approximately 70 fast radio bursts, and then boom, just in a very short amount of time, the population explodes. It's been an absolute game changer in terms of studying these things. And as you can imagine, that's led to some new interpretations of what fast radio bursts are, and some new clues about what these mysterious objects could be. So one of the early breakthroughs after CHIME switched on was the discovery of periodic behavior in a particular fast radio burst. So there was an FRB that was discovered that seemed to go through periods of intense activity followed by silence. And a student I worked with in Toronto was analyzing the data on this source, and she discovered that if you make a periodogram of the activity, and you see there's this strongly favored period of about 16 days. So this is odd behavior, and we still don't exactly know how to interpret it, but the preferred explanation is that the source must be in an orbit with something. But this is the only source that we've seen this kind of behavior in, so we're still not quite sure what this means. It's something we'll have to confirm if we're able to detect more periodic fast radio bursts in the near future. But one of the biggest surprises that CHIME turned up was in 2020, when it discovered a fast radio burst coming from within our own galaxy. So all of the others that had been discovered were billions of light years away on the other side of the universe. This one was right in our cosmic backyard. So this was traced to a type of object called a magnetar, which is a type of extremely magnetic neutron star. So like the neutron stars I was talking about at the beginning, this is magnetars are a class of neutron star. So whether this explanation holds for all fast radio bursts is not yet known. It looks like there are some differences between the ones that are found to repeat and the ones that seem to never be seen again. And could these be two different categories of object? We don't really know yet, but the possibility is something I find fascinating. And part of my research program here at Union is to find a physical mechanism that could link pulsars, magnetars, and fast radio bursts. And one of the ways that I'm going about doing that is by contributing to the development of the upgrade to CHIME, which is called CHORD. So the idea is that if this is CHIME with its 4 half pipes, we're going to build this array of 512 small dishes at the CHIME site that will massively increase the collecting area of the telescope, so making it much more sensitive. But as well as doing this, we're also going to build these like mini versions of CHIME that we call outriggers, where we just have a single half pipe and then a small array of dishes. And we're going to place these thousands of kilometers away from the CHIME site. One of them is going to be about 10 hours drive north from you in Hat Creek, Northern California. So the reason that we're doing this, building these small stations so far away from it, is that we can use this to get extremely precise localizations on the sky of fast radio bursts. So we compare the time that the burst is received at the 3 different sites, and that allows us to triangulate where in a galaxy the fast radio burst is coming from with amazing detail. And a couple of years ago, me and a few of my colleagues built a proof of concept of one of these outrigger stations in the Algonquin National Park in Ontario. So we spent a week out there with some Yagi antennas that we just got from Radio Shack. We mounted them on breeze blocks from Home Depot. We've got this chicken wire on the ground as well to stop the radio reflection off the ground. That's also just from Home Depot. And we built this and hooked it up to Chime all the way on the other side of Canada in British Columbia. And we used it to demonstrate that we could actually do this with the small scale version, of course, but we could get really precise locations from measurements of the bursts that we detected. So while core is in the process of being built, my research group is using existing telescopes to explore links between pulsars and fast radio bursts. And when I applied for the funding that supports this project, I needed a catchy abbreviation. So I've called it EMO-GP, which is short for Emission Mechanisms of Giant Pulses. And this is our mascot. She's a GP, a doctor who is emo. And we take observations with some of the biggest telescopes in the world. And we're doing this to study the physical process that could possibly generate these fast radio bursts. And my team are divided between North America and the UK, and they're busy digging through the data at the moment. So hopefully going to get us close to an answer sometime in the very near future. And that's where I'm going to end. I'll leave this animation running. See if you can spot some of the simulated fast radio bursts. But this is a very new area of astronomy, and we're still working to understand it. But in any case, fast radio bursts are flashes of radio that last a few milliseconds. We see them from across the universe. And it's cutting edge astronomy. Anyway, thank you very much for inviting me, and I'll be very happy to take any questions that you might have. And if you're shy, my email address is there. The QR code will go to my personal website. Just drop me a line. I'll try and answer any questions that you have. Thank you.
Thank you very much, Dr. McKee. What a fascinating research and great presentation you did. Thank you very much. So let me let everybody know that the floor is open for questions. People online can send in their questions from Q&A, and people in person can go ahead and ask. So let's start with in person. Barbara, do you already have people with questions?
Let me inquire. Any questions at this point? Yes. The question was, is there any relationship between the age of the galaxy where these things are being observed and the number of FHBs?
With the age of the galaxy, we don't know yet, because we've actually been able to localize very few of them to individual galaxies, because these things come from really, really far away. So if you think about things like the Hubble Deep Field, where you take a teeny tiny patch of the sky and gaze at it for long enough, you see tens of thousands of galaxies. So if you can only localize something to within a few milliarc seconds of the sky, there's going to be a lot of potential galaxies that it could possibly have come from. So far, we don't have enough that we've been able to make any conclusions about whether they come from a particular kind of galaxy or not.
Thank you. Any other questions at the moment? Do you have any online, Raisa? People are still thinking.
Yes, I do. So the first questioner wants to know, does the duration of the burst constrain anything about the source?
Yeah, the fact that it's so short indicates that it has to be what we call a coherent plasma process, which is one that one that doesn't just happen through like thermal random motion of the material. It has to be probably highly magnetized to keep this amount of plasma in such a small amount of space with a really high energy density. So it implies that these must be coming from very small objects, and it really leans towards these being a type of emission from neutron stars, like similar to pulsars, and like the pardon me, like the one that we traced to a magnetar in our own galaxy.
Thank you. And there is another question. You know, in the public eye, usually radio astronomy are those big 70-meter dishes and stuff. Some of the telescopes you shown were very down to earth, let's call it. Somebody wants to know, is there any chance we can detect these from our own backyard?
I don't think there's any chance you'll detect them from your own backyard, because even though they're bright as far as like fast radio sources go, they're still really, really, really faint. There was plans that I don't know if it ever came to fruition to build like a citizen science thing, kind of like the what was it called? SETI at home. Some of you might remember, where you could download some program and contribute some of your spare CPU cycles to searching SETI data for extraterrestrial transmissions. There was a proposal to make something similar where it would be distributed among everyone's cell phones, so that you could just imagine it as this enormous, fairly weak, but also fairly substantial telescope that could just pick up when these things were happening. You wouldn't get much in the way of like directionality from it. It would be very hard to say where on the sky it came from, but it would help with things like the event rates. As far as I know, that never came to fruition, though. Maybe I'm wrong, and maybe you can download something on your phone to help look for these things.
Okay, great, thank you. And we have one more question here. Is there any possibility of correlating FRBs with events at optical wavelengths?
Well, that's certainly something that's hoped, and there's a lot of really active research going on with that at the moment, where you have things like experiments where a small telescope will shadow a radio telescope just to point at the same patch of the sky and see if it can pick up anything interesting at all when a fast radio burst goes off. But so far there hasn't been anything. It's been a fairly low-key effort, I would say. It's mostly been prototyping, just getting consumer-grade telescopes, hooking them up with some automation for it to follow the telescope, and just reducing the data in real time. I think if someone found something with one of those, though, it would start to be taken extremely seriously, and you probably would get purpose-built telescopes to look for these things alongside the radio telescopes.
Okay, thank you. Barbara, are there any in-person questions?
Any other in-person questions here? Looking for raised hands? Looks like you've explained it all very well. We've certainly been interested. Thank you very much.
And feel free to email me if a question occurs to you later. My address is on the screen there. Just don't be shy.
Okay, great. Last call for questions online and in person. Okay, okay, great. Looks like there are no questions. So are we ready to adjourn? Barbara, anything in person?
Yeah, any last minute things? Nope. everybody's looking attentive, but not like they're asking questions. Again, thank you very much, Dr. McKee. We certainly appreciate the talk. It was really great, really interesting, and I love the animation.
It's
And
great
good
again.
night,
Thanks.
everyone. Thanks again. Yeah, go ahead, Reza.
And let me remind everybody that you could check our calendar on the website for all upcoming events. Okay, bye-bye, everybody. Thank you.